Vapor pressure depends on temperature because at a higher temperature, more molecules can evaporate, and at a lower temperature, less molecules can evaporate. Vapor pressure also depends on the concentration of particles because as the concentration of particles in the solute increases, the vapor pressure of the solvent decreases. Pressure as well as temperature are determining factors for phases of matter because as temperature increases or pressure decreases, substances move towards the gaseous state. As temperature decreases or pressure increases, substances move towards the solid state. Solids have a definite shape and definite volume due to the fact that their particles are relatively close together and merely vibrating, contrary to the popular convention that solid particles do not move. A liquid has a definite volume because the particles are still fairly close together, but liquids lose their ability to maintain a definite shape since the particles are now able to move around semi-freely. Gases are unable to maintain a definite shape or definite volume since their particles are moving around freely and are spaced far apart as the container will allow them to spread. Is the total energy of molecular motion in a substance, while temperature is a measure of the average energy of molecular motion in a substance. Heat energy depends on the speed of the particles, the number of particles, the size or mass, and the type of particles in an object. Temperature does not depend on the size or type of the particles. For example, the temperature of a small cup of water might be the same as the temperature of a large tub of water, but the large tub of water has more heat because it has more water and thus more thermal energy. Celsius and Kelvin are measures of temperature. The way their scales are determined are different, but 273 Kelvin equals 0 Celsius, and 1 Celsius increase is equal to 1 Kelvin increase. A joule is a derived unit of energy equal to the energy of an object undertaken when a force of 1 Newton acts on that object in the direction of its motion over the distance of 1 meter.
Physical equilibrium is the point a substance goes from liquid to gas. At equilibrium, the amount of atoms vaporizing is equal to the amount of atoms being condensed to liquid. As the atoms become liquid, an equal amount will become gas. And if the temperature goes up, the atoms will evaporate. If the temperature goes down, the atoms will condense into liquid. When molecules gain heat, they speed up and move in an unconstrained motion. When molecules are cooled, they slow down and stay closer to one another. When changing phases, if a substance is going from solid to liquid to gas, the molecules gain kinetic energy. If a substance is going from gas to liquid to solid, it will lose kinetic energy. Specific heat capacity is the amount of heat needed to raise the temperature by 1 degree Kelvin, and this is represented by Cp. Heat of fusion is the amount of energy needed to melt or freeze a given mass of a solid, and the symbol for this is HF. Heat of vaporization is the amount of energy needed to evaporate or condense a substance, and this is represented by HV.
There are three main heat energy equations, the first being Q equals mCp delta T, which is energy equals mass times specific heat times change in temperature. You use this equation when trying to find how much energy it takes to move from one temperature to another within the same phase of matter. The second heat equation is Q equals mHF, which means energy equals mass times heat of fusion. This equation is used for finding how much energy it takes to melt or freeze a certain amount of a substance. The last heat equation is Q equals m times HV, which means energy equals mass times heat of vaporization. This equation is used to find how much energy it takes to vaporize or condense a substance. In order to change phases of matter, you must break or form attractions between molecules. Solids have the most attractions, and gases have the least. In order to go from solid to liquid to gas, you must put in energy, usually in the form of heat energy, to break attractions. When you input energy, it is an endothermic reaction. In order to go from gas to liquid to solid, you must take out energy to form attractions, and when attractions form, it is exothermic.
A heating curve is a graph that shows how a substance changes as temperature, represented by the y-axis, and heat energy, represented by the x-axis, go up. The graph starts in the bottom left in a solid state and moves up and right as it heats up. It plateaus at the freezing or melting point of the substance. After the plateau, it transitions to liquid and the line moves up and right again as the substance continues to heat up. It plateaus at the vaporization and condensation point. After this plateau, it continues up and right as its temperature increases and it becomes a gas. A cooling curve is a graph that shows how a substance changes its temperature, represented by the y-axis, and heat energy, represented by the x-axis, goes down. The graph starts at the top left in a gas state and moves down and right as the temperature decreases. It plateaus at the vaporization and condensation point of the substance. The graph then moves right and down after entering liquid phase as the temperature decreases. It plateaus at the freezing and melting point of the substance. The graph again moves right and down after entering a solid state as the temperature continues to decrease. This is a phase diagram for H2O, water. It has 4 phases, 3 of which are shown here. There is a solid region, liquid region, gas region, and the supercritical region, which isn't shown. There are 4 major points on this graph: the normal melting freezing point for water, which is at 0 degrees Celsius and 1 atm, the normal vaporization and condensation point, which is at 0 degrees Celsius and 1 atm, as well as the triple point, which is at 0.01 degrees Celsius and 0.006 atm. The critical point is also shown, which is at 373.99 degrees Celsius and 217.75 atm. This is a phase diagram for CO2, carbon dioxide. It has 4 phases, 3 of which are named here. There is a solid region, liquid region, gas region, and the supercritical region. There are 3 major points on this graph: the vaporization and condensation point, which is at negative 78.5 degrees Celsius and 1 atm, the triple point, which is at negative 56.6 degrees Celsius and 5.132 atm, and the critical point, which is at 31.1 degrees Celsius and 72.74 atm. Phase diagrams are used to find the phase of a substance at a given temperature and pressure by finding the pressure on the y-axis and the temperature on the x-axis, and then looking to see which region on the graph it is in. Phase diagrams can also be used to find the boiling or melting point at a given pressure by finding where pressure is on the y-axis and marking the point. If you're looking for the boiling point, mark the point on the line between liquid and gas, and if you're looking for the melting point, mark the point on the line between solid and liquid. After that, look at the x value to find the temperature for that pressure. Another common use of phase diagrams is to find the triple point of a material. You can do this by finding where on the graph the 3 lines meet.